this is now, I think, our sixth or seventh talk this year, and it's Dario is gonna present tensor products for us, or tensors in general. And he is, just to give a bit of background on him, he did his undergrad in theoretical physics, and then he did his honors in maths, which he says is more like mathematical physics, which probably then led him to do his M in physics, which he's currently busy with. So yes, I think this talk today will be very interesting, and yeah, thank you, Dario, for being here, and we look forward to what you have in store for us.
Yeah, okay, thanks, Rocco. I think in typical physics fashion, my talk is a little bit physicsy in the sense that it's physically applicable, but I hope that the pure mathematicians will at least appreciate some of the stuff. It might not all be new because it's supposed to be aimed at undergraduate, but I hope it's still at least vaguely interesting. So yeah, I'm going to be talking about tensors. I'm going to be talking about, my original title was The Many Faces of Tensors. And just to give you a bit of background or motivation for this talk, there are a few reasons that I chose this topic. I think it's a really cool topic for a talk aimed at undergraduate because tensors are these things that, at least in my undergraduate, I encountered a heck of a lot, but it almost never came with a proper definition. It was one of these things that in applied mathematics or probably computer science and physics, you often see tensors as a calculation tool, and you're never really told precisely what they are. And this was never very satisfying to me, of course, because I was more in the mathematical physics side. And the other thing is, even if you do actually get a definition, if you manage to persuade some lecturer like I did with sufficient badgering to define them for you, the common definition, the one that you're most likely to see, is really, really ugly and incredibly opaque. And I think tensors are a lot deeper than this and a lot more beautiful and elegant if they're properly treated, because there are many more abstract definitions out there. Some of the most abstract and the nicest are phrased in terms of category theory and something called a monoidal category. I'm sure some of you would know about these. But the other thing that makes them good for undergraduate topic, I think, is that they generalize some of the stuff that undergraduates would have encountered, like vectors, linear functionals, and operators. And I think it's a nice generalization. It unifies all of these things. So yeah, what are we actually hoping to set up today? Well, I'm planning to this talk is quite expository. I'm trying to develop the theory that builds up to the definition of the tensor products as sort of the unique space that linearizes bilinear maps. So I might have wanted to put that in quotation marks, but I'll make that slightly more precise a bit later. And we'll eventually build up to the results from category theory called the tensor homojunction, which I think is one of the nicest characterizations of the tensor products and tensors more generally. Because, well, it's really succinct and really quite general. Adjunctions are beautiful. They pop up all over the place. Okay, so I didn't see any undergraduates in attendance, so this is probably an unnecessary preliminary, but I'll just quickly walk through it anyway in case some more have joined. So I'm just quickly revising vector spaces. Obviously, the second years up have seen this. First years would probably not have seen the abstract definition, but it's short enough anyway. So it's just a set equipped with two operations that we call addition and scalar multiplication that satisfy a bunch of axioms. So these four together, we collectively say makes the set into an abelian group with respect to addition. These two are called the distributive laws, the blue ones. That red one is called compatibility of the scalar multiplication with the multiplication in the field, in this case, C. And this one is the identity of the scalar multiplication. So collapsing those abelian group ones, we get this slightly nicer definition, which is just that it's an abelian group together with one other operation called scalar multiplication. Okay, cool. So just notationally in this talk, just to avoid constantly having to say, let X be a vector space, let Y be a vector space, and so on, I'm just going to use the three symbols X, Y, and Z, capital X, Y, Z, throughout the talk to mean complex vector spaces. So if you see them anywhere, that's what they refer to. And then one other thing that I need to quickly mention in terms of vector spaces, perhaps the second years haven't yet seen this, is the so-called dual space, which is just the space for a given vector space X. The dual space is the space of all linear functionals acting on X. So what is a functional? A functional is just a linear map from the vector space into the complex numbers. So linear, remember, means that we can represent it as a matrix in the context of finite dimensional vector spaces. Obviously, there's a more precise abstract definition that you have either encountered or are very soon to encounter if you're second year now. But I like to think of linear functionals as well as row vectors, because if you multiply a column vector, which I'll consider a vector, with a row vector on the left, you get something in the complex numbers. So sometimes we also call linear functionals covectors or row vectors. So yeah, the dual space is just the collection of all row vectors you can think of, or alternatively all linear functionals. And if we have a basis for the original vector space, B1 through Bn, then we have a dual basis for the linear for the dual space, which are those linear functionals defined there. They're kind of the indicator functionals. So given a specific basis vector, they return 1 or 0. This is the Kronecker-Delta sign. They return 1 or 0 depending on whether the two indices match. In terms of columns and rows, if you want to think concretely in terms of bases, which I'm going to try and move away from, then if your basis vectors for the columns are, just the basis vectors, the usual basis vectors with a 1 in each of the positions respectively, then for the linear functionals, it's just the same thing, but for the rows, just the transpose of those. Okay, one more thing I have to set up, in case you haven't seen it, is the idea of equivalence relations and equivalence quotients. So forgive me, there's a lot of exposition here, but I'm hoping that most of this is just background that you would have already seen. But an equivalence relation is just a relation that is a collection of pairs that satisfies three main properties: reflexivity, which is that everything is related to itself; symmetry, that if x is related to y, y is related to x; and transitivity, which tells us that if x is related to y and y to z, then x is related to z. Now, equivalence relations are designed to sort of mimic a notion of equality, to tell us that some things are equivalent up to some identification. So one of the first places you might encounter them is when studying the modular arithmetics. So addition modulo, say, 5, and multiplication modulo, say, 5, where you identify all the numbers together that have the same remainder when divided by 5. So that identification, taking an equivalence relation and kind of factoring it out, that's called the quotient. And indeed, we can do that with a vector space as well. So if we have a vector space, okay, yeah, so here I've first written it for a set. We can take an equivalence class, which is all things equivalent to x, and then the quotient space is just the collection of all, or the set of all equivalence classes. So for a vector space, we can take that quotient space and equip it with a product and a sum. Of course, we need to check that these things are well defined. If you don't know what that means, don't worry too much about it for now. It's just essentially a formality, but we can define a vector space. That's the quotient space. So essentially, it's the same as the original vector space, but where everything that was considered equivalent under the relation is kind of lumped together in a single object. Okay, cool. Now we actually get on to the main content. So with the preliminaries out of the way, what is a tensor? So this is the first definition of tensors that probably most people encounter. And I really hate it. And I don't know if I actually have to say why I really hate it, because I think it's quite apparent. I think any sensible human being who looks at this definition automatically hates it. But it's quite common. And this is probably the only one that you'll manage to get out of a physics lecturer, at least most physics lecturers. So a tensor of type PQ is a multi-dimensional array with P upper indices, which I've called I, and Q lower indices, and it's associated with a chosen basis B, such that under a change of basis, this is a change of basis transformation here, these P matrices represent the change of basis matrix, the components transform according to this disgusting mess over here. In order to make it slightly less disgusting and less of a mess, I've color-coded the indices, so these blue indices over here correspond to these ones and these red ones to these. And something else I should mention is that we're using what's called the Einstein summation convention, which is whenever you see a repeated index on one side of the equation, that index is implicitly being summed over. So for instance, in this change of basis transformation here, where we have bi p superscript I subscript 1, that's implicitly a sum from I equals 1 up to n. And on the right-hand side of this component transformation of the tensor, there are many sums. There's a sum, p sums on the I1 through IP, and q sums on the J1 through JQ. Anyway, what on earth is this actually saying? It's incredibly opaque. So let's unpack it a little bit. In particular, let's look at a few sort of very simple examples and see what we can make of it. And hopefully this will let us generalize, and that's the idea. Okay, so the first one is let's look at a tensor type 1, 0. So P is equal to 1, Q is equal to 0. So I've copied down the definition again in the specific case. So in this case, it's a one-dimensional array indexed by a basis and with a superscript I, or I1 if you prefer, which under a change of basis transformation transforms according to this law. Okay, take a second. Well, it's not immediately obvious necessarily, but this is actually just the transformation of a regular vector. We call it the contravariant transformation. Contravariant meaning the bases transformed, or the basis vectors transformed according to the matrix P, and the tensor transformed according to P inverse. So that's called contravariance. There's a more abstract definition of that, but for our purposes for now, that'll do. So, okay, you might not notice that this is actually a change of basis for regular vectors, but it is. So just to quickly refresh your memory, here's the change of basis matrix. It's defined as the matrix where the columns are each of the vectors in C represented with respect to the basis B. Now, the basis vectors here are transforming in such a way, right? If you read off one of these columns, we fix the column number J, the column index J, and we walk down the rows I. And that gives us the coefficients of expansion with respect to the B basis for each of the Cs. So that's where this equation here comes from, so straight from the definition. And we identified this P matrix here in the notation P transformation from C to B as the P referenced above. Okay? But now the coordinates transform, of course, not according to the change of basis matrix from C to B, but rather the change of basis matrix from B to C, which is the inverse. So you see that that is actually the same as this transformation law up here. This is sometimes, in physics, we sometimes call this the distinction between active and passive transformations. I don't like that terminology, but anyway, it's just noticing that if the basis vectors transform in one direction, the coordinates transform in the other. Okay, so what's a tensor of type 0, 1? Well, here it's a one-dimensional array with a single lower index, J, such that under a basis transformation like that, it transforms according to this law. Okay, whatever. You might not notice, but this is just the covariant transformation, covariant meaning that they both transform according to P, of a linear functional or a covector, or rather the coordinates of that linear functional with respect to the dual basis. So the components, remember, of the linear functional with respect to the dual basis are computed like this. Each component is linear functional applied to the respective basis vector. Right? If you think about the definition of the dual basis in terms of that Kronecker delta, this is how you'll get the coefficients on those indicator functions. Okay, so the basis vectors transform like this. That's the same line as on the previous slide. And hence, the components of the linear functional are simply f applied to the new basis vector, which is f applied to this contraction. We call that a contraction. And that is simply P times f applied to, to the B basis vector at index I, which is just the original coordinates. So you see here, this is the same transformation law as above. Okay, so tensors of type 1, 0 are vectors, or column vectors rather, and tensors of type 0, 1 are covectors or row vectors rather. So what's a tensor of type 1, 1? Well, it's a two-dimensional array with one upper index and one lower, which under change of basis transformation changes according to this conjugation law over here. And this is just the transformation law of a linear operator, or a matrix rather, in component form. This is probably not news to you, but it's essentially just taking the previous examples and sticking them together. If we have the components of a linear operator, then when we compute them with respect to the new basis and we use the previous two examples, we get the one factor of P inverse and the one factor of P. Okay, so tensors of type 1, 1 are matrices. Cool. So our examples have suggested that contravariant or upper indices behave like vectors, and covariant or lower indices behave like covectors, or at least covector components. So now the natural question that we might ask is this: we saw that a type 1,1 tensor behaves like a matrix. So does that mean that we can view a matrix in terms of vector and covector pairs? And the answer is yes, absolutely. This is what's called the singular value decomposition of the matrix, which is one of many matrix decompositions. It's theorem 7.14 in the standard linear algebra reference for undergrad, which is Poole. And it's this theorem over here, which is that an m by n matrix of rank R, where R is some number less than equal to n, may be written in this form, where we have an expansion of these sigmas times, this is a column vector times a row vector. So each of these is an operator, because you can think of it acting on a component over here, or on a column over here, which would first hit it with the row vector, which is a linear functional, and then hit it with a column vector, which will give back a new column vector. So this is a linear operator, or a matrix rather. And these sigma I are called the singular values of A, and there's a really nice efficient algorithm for computing them. So yes, we can indeed think about a matrix as not just a single vector covector, but rather a sum of vector covector pairs. Okay. Cool. So now let's try build towards a more abstract definition, given everything that we just saw. And this is going to be via the tensor product. So far we've talked about what a tensor is. Now I need to tell you what a tensor product is. And it turns out the two are intimately connected, but we'll get to that. But first I need to quickly set up what the free vector space is. So the free vector space is a construction that lets us create a vector space with any given basis. So you give me any set, and I give you back a vector space that has that set as a basis. And you can think of this, probably the most common way of thinking of this is you just take formal linear combinations of things from that set. So if your set contains a bunch of elements, then an element of the free vector space over that set is quite literally just some formal, by formal I mean symbolic, expansion of coefficients times things from that set. And of course, then we impose some rules on those formal expressions that make it behave in a way that a regular vector space does. It's a little bit difficult to set up what those rules are in a precise way because they're rewriting rules. So a slightly neater definition, but perhaps less intuitive, is it's the set, the vector space of complex valued functions of finite support on the set, with the usual addition and scaling, I say. By that I mean the usual addition and scaling of functions. These are functions. We know how to scale and add functions. What do I mean by finite support? In case that terminology is never seen, finite support just means that the function is 0 on all except finitely many elements. So there are finitely many things from the set for which the function is non-zero. Okay, how is this the same as the formal linear combination interpretation? Well, it's actually a really simple correspondence. In the formal linear combinations, we just think about the function as giving these, the complex valued function as giving these coefficients of the expansion. And of course, there are finitely many non-zero coefficients precisely because f has finite support, and that's why it has to have finite support so that we don't end up with linear combinations that are infinitely long. Okay, so with that out of the way, that's the free vector space. We can finally get to the first slightly abstract definition of the tensor products, and I've even titled it an admittedly only slightly more elegant formulation. But okay, the tensor product is the quotient space of the free vector space of the Cartesian products of the two vector spaces with respect to the equivalence relation generated by these equivalents, or by these relations over here. Okay, good grief, that's a lot to parse. So what do I mean by equivalence relation generated by those relations? What I mean is simply take those relations and add to it every other relation that you need in order to make the resulting relation satisfy the three axioms of an equivalence relation. So that is, it must be symmetric, transitive, and reflexive. So basically the equivalence relation generated by it is the smallest equivalence relation containing it. Okay, cool. So take the equivalence relation generated by this mess. What is this mess? Well, you see what's happening here is that this lets us associate things that we want to be equal in the tensor product. So what we're saying is in the tensor product, if we have a pair of vectors, x1, y, and a pair of vectors x2, y, and we add them together, we want that formal linear expansion in the free vector space to be associated with the single pair of vectors x1 plus x2 comma y. In other words, we want our formal linear expansions of pairs to be linear in the first argument. And the same thing, of course, for scalar multiplication. We're saying that if we ever have a formal expression of the form lambda times some pair, then we want that to be the same as an expression of the form a pair where the lambda has been absorbed into one of the vectors. So this is just imposing, kind of by brute force, mechanically imposing linearity in the first component. And then the ones on the right-hand side here are precisely the other components. So this is just mechanically imposing linearity in the second component by directly identifying underneath this equivalence relation formal linear combinations that we would want to be related if this thing was linear in the second component. Okay, so really what the space is it's a bunch of pairs of vectors in the form x comma y, where x comes from x and y comes from y, all added together with coefficients, scaling coefficients, where we make the following identifications, and whatever other identifications we need to make in order to make it into an equivalence relation, right? Which also makes it symmetric and transitive and all that. And then we have a special notation, which is that we write, we use the same symbol. This is called the tensor symbol, or some people call it the tensor product itself. We use the same symbol to represent the elements. So remember I said that things inside inside a quotient space were these equivalence classes, which we use the square brackets to represent. So the equivalence class of a pair is instead written with this notation, x tensor y. So when I say equivalence class, remember, I just mean everything equivalent to x comma y. Equivalent under what? Equivalent under these identifications that identify things that are the same under linearity, which we've imposed, yeah? Okay. Cool, so then what's a tensor? If that's a tensor product, well, now we can say that a tensor of type PQ on X is just a vector in this tensor product. So, okay, there's something I haven't shown here, which is I've only defined the pairwise tensor product, and I haven't shown that it's associative. So really, I'm cheating a little bit by dropping the brackets here, right? Because I've written this tensor product as P plus Q things, but really, I haven't actually checked that I can bracket them in any way. But I can, and I'm going to continue to cheat as such. But a tensor then of type PQ is just a vector inside this tensor product, where we take P copies of the vector space and Q copies of the dual space. So now, all right, this is a lot of abstract jargon. If you haven't seen it before, at least I'm sure it's quite overwhelming. But the important thing is that this actually is exactly what we observed in the concrete case, right? Because what we observed in the concrete case was that these contravariant indices, the P indices, the upper indices, acted like vectors, and the covariant indices, the Q, the Q indices, the lower indices, acted like covectors or linear functionals. And that's exactly what this definition here makes explicit, right? We have P copies of the vector space and Q copies of the dual space. So now all that remains for us to really truly connect the two definitions is to explain how we get those components. And it turns out that they're just expansion coefficients with respect to a basis of the tensor product. So let's quickly write down what a basis of the tensor product looks like. Okay, so given bases for x and y, b and c, consisting of basis vectors b1 through bn and c1 through cn, the basis vectors for x tensor y are just the tensor products of each of those pairwise vectors. We've kind of forced this to be the case by choosing this particular definition in terms of an equivalence relation or an equivalence quotient. So the proof is really short, ultimately, but let's quickly step through it. So to see that those vectors there are linearly independent, all we have to notice is that two pairs of the form bi prime, or sorry, bi cj and bi prime cj prime are inequivalent whenever I and j are not both equal. Because of course, them being inequivalent tells us that the resulting pairs are not linearly dependent, because that equivalence was exactly what imposed linear dependence, right? We imposed linear dependence via that equivalence relation. And of course, they're not equivalent, because otherwise, if they were, then we would have two linearly independent vectors, two linearly dependent vectors in one of the two bases, because each of these equivalence relations was with respect to one component. Okay? So the basis vector's linear independence translates directly to linear independence of the tensor products of the bases. And then the other thing that we need to check is that it spans. Well, that's easy, because the general element of the tensor product is just some linear combination of these tensor products with some coefficients lambda. And we can expand each xi and yi in the bases. So xi gets expanded as some combination of the b's, and yi gets expanded as some combination of the c's. And then we just use the linearity of this tensor product. Linearity meaning that we can pull all those expansion coefficients out of the tensor product into coefficients that sit in front of the whole product. And what we're left with is some linear combination of just the basis vectors tensor product. So I hope this makes sense. Are there any questions at this point? Okay, good. So with that out of the way, given that that's the basis for the tensor product, what are the components? Well, like I said, they're just the expansion coefficients with respect to the spaces. In particular with respect to the induced basis on here, because we have a basis B for X, so that gives us a dual basis B, B star, say, for X star, for the dual space, and then we can just use those basis vectors to construct the basis for the tensor product, and that's exactly where these expansion coefficients here come from. Okay, and now the transformation law just falls right out, right? I haven't actually derived it here, just because I think it's more messy than it's worth, but we've basically already seen it, right? We've seen that coefficients of vectors acquire a prefactor of a P inverse, and coefficients of covectors acquire a prefactor of P. If you write that out formally in this case, you'll pick up a P inverse for every one of these B's and a P for every one of these betas, and like, hey presto, you've already got back to this transformation law over here, where we have a P inverse for every one of the upper indices and a P for every one of the lower indices. Okay. Cool. Now we can talk about rank. So an elementary tensor, or a rank 1 tensor, is just one that can be written as a single term. So a tensor product of just some vectors and covectors, but without a sum. And then the rank of a tensor in general is just the minimum number of such elementary tensors that you need in order to obtain the resulting tensor, T. And I hope you see this coincides exactly with how the matrix rank, which remember was defined differently in the context of matrices, at least seemingly differently. The matrix rank was defined as the dimension of the row space, or the dimension of the image if you want. And the matrix rank enters the singular value decomposition, that theorem that we saw earlier, in the way that a rank R matrix was expressible as a sum of R terms of this form, each of which now we notice is elementary. So we see that that's actually the same notion of rank as in the more general tensor context, yeah? Because in the more general tensor context, it's precisely the number of terms in that expansion. Okay. So now to talk about some of the even more elegant definitions that don't require just as much like brute force identification, but rather come out of more familiar concepts. I need to introduce one, which is a bilinear map and a bilinear form. And it's really not very difficult because you know what a linear map is. Well, a bilinear map is just a map that is linear separately in each of its arguments. So I've written out that formally over here, but it's really not terribly hard. It's linear with respect to the first component, it's linear with respect to the second component. You might recognize, for instance, that the dot product or inner product is linear with respect to each of its components. So that's an example. And a bilinear form is the same as a bilinear map, but just where we take the codomain to be the complex numbers. So it's just a bilinear map into complex numbers. Just like a linear functional, remember, was a linear map into complex numbers, a bilinear form is a bilinear map into complex numbers. And notationally, I'll write bx cross y comma z for the space of all bilinear maps, and I'll just omit the z when it's bilinear forms. Okay, so remember what we found? We found that linear functionals were type 0, 1 tensors, and later we saw that in general, this Q over here in the type generally refers to the number of copies of the dual space that are present in the tensor product. So it should come as no surprise that we can think of bilinear forms, just like we thought of linear functionals as type 0, 1 tensors, we can think of bilinear forms as type 0, 2 tensors. And this actually motivates the definition of a tensor product given in G1G, one of the references I use. And this is actually used to define the tensor product. So we've kind of come full circle, right? We've observed that they behave in this way, and now we're using this as the definition. And that's sort of the theme for this talk. So the tensor product in G1G is a subspace of bilinear maps defined on the Cartesian product of the dual space of X with the dual space of Y, spanned by bilinear forms. Sorry, did I say maps? I meant forms, defined as follows. So, okay, this is a space of bilinear forms. So everything in here is a bilinear form. So X tensor Y in particular is a bilinear form. What does it act on? Well, it acts on a pair of linear functionals. That's this F and G over here. And how do we define a bilinear form? We have to define it on every pair. And what do we have to get? We have to get a complex number. So how do we get a complex number out of F and G together with X and Y? Well, we can just take F of X, which is a complex number, since F is a linear functional, times G of Y, which is a complex number, since G is a linear functional. So this is a well-defined definition. But there's a different one in a different textbook. And there are actually a lot of definitions of tensor products, which is one of the frustrating things if you try to read about them, and part of my inspiration for this talk. There's a different definition in Ryan, which is instead of the bilinear forms on X star cross Y star, it's the linear functionals on bilinear forms. Now, I mean, maybe if you are mathematically mature enough, you might see this and think immediately, oh, well, that's obviously isomorphic. And well, yeah, they are. It's not necessarily so obvious because the one can be embedded in the other, but it's the fact that we say that it's spanned specifically by these functionals over here that means that they are indeed isomorphic, but we'll get to that in a second. So, okay, what are things inside here? Well, they're linear functionals. What do they act on? They act on bilinear forms. So take a representative bilinear form F, and we need to get back a complex number. Well, we can just act F on X and Y. Okay, cool. So we have two definitions. I like the second one more, the one of Ryan. So let's stick with that one and see if we can work back towards the other one. So in order to do that, we come, first of all, via the results, which I've called linearizing bilinear maps. And this is actually one of the most important facts of this whole talk that I'll reiterate as we get to the end. So consider Ryan's definition, right, where a tensor is a linear functional acting on bilinear forms. Now, take a bilinear form. Let's call it capital F. And we can produce from it, I claim, a linear functional, right, which I've called F tilde, defined instead of on the Cartesian products, like the bilinear form is, we define the linear functional on the tensor product. And we can define them on a basis. So take one of the representative basis vectors, let's say X tensor Y, and we define it as such. We define F tilde of that tensor, rather, is the tensor acting on F. And what do I mean by that? Well, remember, the tensor was defined, according to Ryan, as a linear functional acting on bilinear forms, right? So we have a bilinear form, capital F. So this linear functional can just act X tensor Y on capital F, which according to Ryan was defined as such, F of X comma Y. So from a bilinear form, we've obtained a bilinear functional, but instead on the tensor product, instead of on the Cartesian product. And we can go the other way. Similarly, if we take a linear functional on the tensor product, we can produce a bilinear form just by chaining that linear functional together with the bilinear map that takes us from X comma Y to X tensor Y. That map is bilinear. It's easy enough to check that. So from bilinear forms, we've obtained linear functionals on the tensor product. And from linear functionals on the tensor product, we've obtained bilinear forms on the Cartesian product. And this is really the central connection. We can take it one step further. So I said, hence the bilinear forms on X that should say x cross y, sorry. Did I leave out a cross? Yeah, I changed notation suddenly without noticing, sorry. That should say b of x cross y. The bilinear forms on x Cartesian products y are in bijection with the dual space of the tensor product. But we can go one step further, right? Why stop at bilinear forms? Let's linearize bilinear maps. So just it's the same story, right? Take any bilinear map, just instead of going into C now, it goes into some arbitrary vector space Z. And from this, we can produce a linear map, which I've called A tilde, on the tensor products, which I again define on a basis in basically the same way as over here, right? Over here, I defined F tilde of the tensor products was F of the pair, and here A tilde of the tensor products is A of the pair. We have to do a little bit more work here because this isn't how we defined the tensor products in the beginning, so we need to check it for well-definedness, but it's not too hard to do. The reference for that is in Ryan, if you'd like to go look at how he does that, how he does that. And then once again, we can go the other way, take a linear map, and we can produce a bilinear form, a bilinear map, sorry, in the same way as how we did above. Okay, so I'm going to pause here for just a second, because this is the very important point that bilinear forms and bilinear maps, or bilinear maps and linear maps are in bijection. Bilinear maps on the Cartesian product and linear maps on the tensor products. So now we can link our definitions together. We can first of all link them, and I haven't actually gone through this argument in the slides, but we can link them by noticing that they're both isomorphic to the quotient space definition individually. Because they are manifestly spanned by pairs of vectors, just like the quotient space was. And of course, they are both bilinear, so they satisfy the quotient relation. So we can write down some pretty obvious linear maps that turn out to be isomorphisms. Just in case there's anyone watching who doesn't know what an isomorphism is, it's a linear map that's invertible and whose inverse is also a linear map. And we use isomorphisms to say that vector spaces are kind of the same, because a linear map, remember, is a map on a vector space that's kind of structure preserving. It remembers the structure of the vector space. So by finding a bijective structure preserving map, we have that two things have the same structure. In the context of the vector space, that means if we find a linear map that's invertible, the two vector spaces can be seen as just the same, in the sense that you can take one thing from the vector space, from one vector space, and rewrite it with different notation in the other one, and they'll behave in the same way. Anyway, that's not terribly rigorous, but you can look up what an isomorphism is if you've never heard of one. But we can write down linear maps that turn out to be bijections, and they're kind of the obvious ones, right? We just send x tensor y to the pair in the quotient space, x comma y and vice versa, and they are linear, and that's easy to check, and they are invertible, and that's also easy to check. But I think the more elegant way of linking at least these two definitions, the one by Ryan and the one by Givenchy, is to use this property that we just explored, this property that the bilinear maps and the linear maps were in a one-to-one correspondence. So what we can notice is, okay, just to avoid ambiguity, let's use subscript R for Ryan's definition and subscript J for Givenchy's definition. The map exhibited by Givenchy, which takes a pair to its tensor products, that is the tensor product in Givenchy's definition, which lives, remember, in bilinear forms on the Cartesian products of the two dual spaces, is bilinear. And because it's a bilinear map from the Cartesian products, what we found is that there's a unique linear map from the tensor product, from Ryan's tensor product into it. Right? That's exactly what we just demonstrated. For every bilinear map on the Cartesian products, we have a linear map on the tensor products. And we can easily show that this bilinear map, that this linear map is injective, and so Ryan's space embeds into Givenchy's, and indeed it's isomorphic to the space spanned by the vectors that Givenchy used to define his space. Yeah, some details left out there. Once again, it's in the references, but I think the key idea here is quite clear, which is that we've used this unique association between bilinear maps and linear maps. And we can make this a little bit more abstract by formulating it in terms of what's called a universal property. So those of you who have seen any category theory before have no doubt encountered one of these. because they're sort of central to a lot of category theory, and they crop up, like I said, absolutely everywhere. They're used to define things like products and sums and generally co-limits and limits. But basically, here's how we formulate it in this context. We can define the tensor product as the vector space, the unique vector space, I should say, and the associated bilinear map, that is the one that sends x comma y to x tensor y, that satisfies the following universal property. Okay, what is the property? The property is this. For all bilinear maps on the Cartesian product, there exists a unique linear map on the tensor products, such that this diagram commutes, meaning if you first apply this map that sends the x comma y pair to x tensor y, and then apply the linear map, you get the same as if you apply just the bilinear map from the start. So this is really the abstract way of formulating this, right? These bilinear maps psi are in a one-to-one correspondence with these linear maps h. And of course, we can just write, yeah, that's what I said. Phi is the map sending x comma y to x tensor y. Right. Now, what's really cool about this definition, and this is general for all definitions like this in terms of universal properties, is that it defines the tensor product uniquely up to isomorphism. So how do we show that? Well, suppose that there's some other vector space that satisfies this universal property together with its associated maps, as omega is filling in for the place of phi. And then we can just construct the following diagram where we keep the phi and we throw the omega in the place where psi was, right? Now, this diagram gives us two unique arrows by the universal property. It gives us this linear map H down to here because omega is bilinear, and it gives us a linear map G up to the tensor product because this map phi is bilinear. And we said that they both satisfy that universal property. So we get these two linear maps that make the diagram commute. In other words, phi composed with H is the same as doing omega, and omega composed with G is the same as doing phi. And if we just stick those two equations together, we see that G composed with H is the identity on phi of x cross y, which is a spanning set for the tensor product, and so it's the identity on the tensor product. And similarly, H composed with G is the identity on this spanning set, and so on the tensor product. And hence, the two are inverse to each other. H is inverse to G. So we found an isomorphism between these two spaces, and hence, the tensor product is uniquely defined by this property up to isomorphism. So I think that this kind of proof is really beautiful. Category theory is full of proofs like this, but I love this characterization of just about anything. I love to characterize things in terms of tensor, universal properties if I can, but tensor products in particular are wonderfully characterized here because they give us this real notion that the whole idea behind a tensor product is to linearize bilinear maps. Okay, now I'm going to step a little bit outside of the scope of an undergraduate talk because I haven't actually defined a category or any category theory topics, but this is just one slide, so stay with me. If you don't follow anything on here, then that's totally fine. It won't last very long. But I just wanted to remark that one of the most famous algebra textbooks is that by Lang, and Lang gives a definition kind of different to all the ones that I've given, at least on the surface, which is he defines a category where we have bilinear maps as objects, and morphisms are the linear maps H that make the following diagram commute. And then his definition of the tensor product is just an initial object in this category. That is an object that has a unique morphism to every other object. Now, I say that these two are different, but really they're not. This is just a simple rewriting of the last definition in a different language. It's quite clear to see that as long as we identify this map from here to Z with the tensor product itself, with Z, then these are actually saying the same thing. They'll give the same object. You don't actually need to be a category theorist to see that that's true, as long as you have any vague idea what objects and arrows are. But the other thing is that, and this is something I wasn't able to fully research, this harkens to a connection between universal arrows and universal objects in the comma category. But I'm not 100% sure that this is actually a universal object in the comma category because these are multilinear. There are somehow multi-morphisms, and I'm not sure if you can construct comma categories in that way. I'd be interested to hear if anyone in attendance has some insight there. But yeah, at least it harkens to that connection because it's the same sort of definition used in, what is it called? I think the co-slice category to define universal properties in terms of some universal objects. Anyway, I'm not going to dwell on that for terribly long. So the last property that I want to point out, and this is, I think, the most elegant formulation that we have of the tensor products in general, at least outside of going into monoidal categories, is if we write hom xy, so the set of linear maps from x to y, and I'm also going to abuse notation slightly by using the same notation to refer to the vector space of linear maps from x to y whenever it can be interpreted as a vector space. Formally, we would call that the internal hom functor, and it's slightly different to just regular hom, but for our purposes, they can be seen as the same. So write hom x comma y is the set of linear maps, or the vector space is linear maps. Well, then we can interpret a bilinear map as a linear map into the hom set of the latter two spaces. In other words, we can associate a map that is linear in x and y with a linear map in x that goes to a linear map in y that goes eventually to the original bilinear map's image. This is sometimes in computer science called currying in the context of regular functions on regular sets. And in this way, we can identify bilinear maps from x Cartesian products y into z with linear maps from x into linear maps from y into z. So hom x comma hom y comma z. And then this allows us to give the most succinct formulation of the linearizing property that we've seen so far. And this actually encodes the same thing as the universal property. That whole big diagram, this universal property over here, encodes the same information as this succinct statement that we're about to see over here, which is the so-called tensor homojunction, which is just the statement that the hom sets are in bijection. The set of linear maps from x into linear maps from y into z, thought of as a vector space, is in bijection with a set of linear maps from x tensor z, y into z. And the way that we would say this in category theory language is by saying that this functor where we leave out the left components, this what we would call the tensor products, but on one side, is left adjoint to the internal hom functor, which is this one where we leave out the second components of the hom. But yeah, don't worry about that last sentence. The equation is the most important. Okay, so I'm almost out of time. I wanted to briefly take a sidestep into a few areas in physics where we sometimes encounter tensors, just to explain why I, as a person now studying physics, am so interested in them. So we encounter them in classical mechanics most commonly. For instance, we have the stress tensor, which is just a nine-component, two-dimensional tensor that gives the traction from a normal vector. We also have others that I didn't include here. For instance, in relativity, we have what's called four vectors, which are a kind of way of unifying coordinates for space and time. And they transform with respect to something called the Lorentz tensor. In general relativity, we also have a metric tensor that is space-dependent. That tells us basically how space and time curve at every point in space-time, because space-time curves in general relativity. And that's described according to a tensor equation. Essentially, all of relativity is in terms of tensor analysis. And then the other application where it comes up is in tensor product space in quantum mechanics. So in quantum mechanics, we describe the system as having a finite, well, not always finite, but often discrete. Okay, it's neither of these things in general, but it's often discrete set of states. The point is it's a Hilbert space, which is just a vector space with some extra stuff. Those who know what that is will appreciate why I'm leaving that out. But it's just a vector space. And if we take two systems together, then their collective Hilbert space, the set of states that the two systems taken as a whole can be in, is the tensor products of the individual systems Hilbert spaces. Now, why this is interesting is because it leads to the property called entanglement, where the outcome of a measurement of one element of the system can greatly and instantaneously influence the outcome of the measurement of a different element of the system. And this arises precisely because of higher rank tensors, precisely because every tensor is not necessarily elementary. I'm not going to make that connection entirely clear because I can't really define all of the stuff in quantum mechanics to get to it, but essentially it comes from that. Okay. So yeah, I'm just about out of time because I'd like to move into questions. So the key takeaway is multilinear maps on the Cartesian products are in one-to-one correspondence with linear maps on the tensor products. And we can represent this succinctly with a single equation called the tensor homojunction. That's that equation there. And of course, we saw some examples of tensors, including from physics. And then, yeah, that's my reference list. And thank you for listening.